Great. Well, welcome everyone. It's my pleasure to introduce the Research Council member, Dr. Laura Freeman from Virginia Tech. She'll be presenting updates on the research task ART-007, Cognitive Bias in Intelligent Systems. And with that, I turn it over to you, Dr. Freeman.
Thanks, Tyler. Hopefully everyone is seeing, looks like you're seeing my screen here. So as Tyler noted, the task is actually called Cognitive Bias in Intelligent Systems. But one of the things that when we started down the path of this research, as often happens, is we realized we don't have some of the foundations in place to be able to do things like measure cognitive bias. How do you defining bias and what defining what cognition is or what an intelligent agent is. Those are some of the things that I had to tackle before we got started on this research project. And so you'll see the title of the slide that I have here is Performance Measures, Environments, Actuators, and Sensors. PEAS, it's a term from Russell and Norvig in their textbook, Artificial Intelligence, and thinking about how we incorporate these PEAS, the performance measures in particular, on which we would measure any biases, into testing autonomous intelligent agents is kind of where the research progressed over the course of the year. So I would like to acknowledge the team that I worked with on this research. It was a collaboration between my group at Virginia Tech and Dr. Jitesh Panchal's group at Purdue. Because of the complex and interdisciplinary nature of this research, I'd like to also call out the diversity of people we have on our team. So Melanie Grande, she's now at NASA. She's a satellite expert and working with them. Andrew Lang and Adam at Purdue were in systems engineering, mechanical engineering with Jitesh. At Virginia Tech, I had Ivan Hernandez, who's actually in psychology working with me on this, and Scott Welsh, who's a machine learning researcher. And so we had a very interdisciplinary team putting together this research over the course of the year. And as a result, I think we came up with kind of a solid framework for thinking about how you do test and evaluation of autonomous intelligent agents. So with that, I will launch into the talk. First, I'm going to talk about this test and evaluation framework that we developed for thinking about kind of the process, the data collection techniques, when you would want to execute this process in the acquisition lifecycle. Excuse me. And then the second part, I'll do a deep dive into performance measures. So after we went through kind of what we would want to do in terms of test and evaluation, the sponsor was really interested in, okay, well, can I actually measure that? What does performance measure development look like for these types of systems? So we developed a kind of a process that follows block diagramming techniques to define performance measures at all levels of the system. So everything from the algorithm up to the mission context. And then I'll wrap up with kind of a summary of what we did in the first year of this research project and potential future directions at the end. So let me start by giving you a motivating example, a motivating kind of use case, if you will. So this is as we brainstormed on ideas, kind of what we settled on as our motivating framework for thinking about this test and evaluation framework for autonomous intelligent agents. And so if you think about the satellite networks that we have today, one of the big tasks that they do is they observe Earth. And so we might want to observe Earth to do things like detect illegal fishing or maybe illegal events like human trafficking. And so there's the wanting to observe Earth on the sea, but also when we get to the use case later, it was a very active fire season in the United States. You could also think about wanting to observe fires and detect when there's new plumes and track how they progress and move. And so we'll use those as our two motivating observation case studies. And so we have networks of satellites that we currently use to do these things. And the question is, if we start to replace some of those satellites and their key functions and where humans make decisions with intelligent systems, so leveraging machine learning and artificial intelligence, how do we know that we've done that successfully, that we had an improvement in performance over what humans were capable of? How do we track that performance and understand the risks associated with it over time? and then across a very diverse operational space. So the performance measures are what we'll use to understand how the system, the algorithm, the system, and the systems are performing, but they have to execute these tasks in the environment. So the environment is everything from where they are in space, any kind of environmental factors that they have to deal with, debris, um, weather, anything that uh, restricts their field of vision on Earth, um, all of those types of things, as well as any kind of external environment attacks. So from everything from the purposeful to the just space debris that could take out a satellite or knock it off orbit. In kind of the space and cyber domain, as well as on the ground. If someone's participating in a human trafficking activity that they want to hide, they might be pursuing techniques of camouflage and distraction or deception. And so that's the environment that we have to contend with and think about when we're thinking about a test and evaluation framework. And then what the satellites can do, those are their actuators. So they can move to new locations in space. They can retask and assign observation tasks to other satellites. Those are the actuators that we're dealing with. And then we think about the sensors as their ability to observe the Earth. So that's kind of an overview of the universe that we will use to define our test and evaluation framework. And the question is, how do we get from this concept, ConOps, to, okay, we're actually going to go do this. We're going to go design and build a system that we're going to put in space. How do we go through the acquisition strategy? And so the next slide that I've got is really what we call the Vtp model, where the V is the systems engineering V that many people that are attending this are very familiar with. So how we go from the requirements and analysis all the way down to the detailed design, and then back up on the other end of the V, implementing that, and then doing unit testing at the algorithm level is how we think about it here, moving up into an integrated system, and then finally full up system level testing. And so that we say is all still important, and we'll talk about kind of the approaches that we designed to develop test strategies there. But the thing that we think is critical is you start to incorporate learning algorithms in complex systems is that the test and evaluation process doesn't stop at deployment. There are first going to be these, you can see the slices as we're kind of defining them as unique opportunities to do test and evaluation, but also the need for a feedback loop and kind of continuous observation. And so as part of our framework, we've defined that might be things like the mission objective change. So if we're moving from observing sea and looking for illegal fishing or illegal trafficking events to this forest fire concept, but all the data that we've trained, maybe a computer vision algorithm was really focused at the sea environment and detecting kind of unique sequences of things that would be indicative of a trafficking event. And now all of a sudden we're looking for fires. We might be using a lot of the same sensors, but the data that we've trained them on will need to be updated. And so we'll want to do another iteration of our test and evaluation process to make sure that we've made that mission change successfully. Also, if there's things like payload degradation, you lose a satellite in the constellation, how do you rejigger and understand that you haven't lost capability? That's another unique event that might drive a test. And similarly, an adversarial attack, how do you reassure or regain confidence in the system? And so we wanted to highlight that this test and evaluation process goes on even after fielding with these intelligent agents. Now, when we're in the systems engineering V piece of this, and we're actually building up the system, and then actually into execution as well, I like to think about this hierarchy of tests that is needed. And so first of all, we could have completely digital simulation where it's a completely simulated environment, and we're looking at how do we structure the requirements and what performance measures make sense there. The next level up is software in the loop. And so maybe here we're integrating our AI algorithms and want to know how they are going. And we're characterizing all of the environment, the actuators, the sensors, all of those things are being characterized in a digital simulation, but we're actually using the software that would be embedded in the system. And then we take the algorithm and we actually embed it in the system. Maybe we have it in the lab and we're feeding it kind of simulated images, but it is actually, using the processing power on board the satellite, those kinds of things, moving to any ground testing, and then finally deployment into space. So it's important when you're thinking about what makes an adequate test as you go through this hierarchy, is that as you're going up, you're getting more and more fidelity in terms of reflection of the actual operational mission. But as you go down, it's cheaper to collect more data and have more control of the test space. So in a digital simulation, I can set up any environment that I want. Whereas when I'm actually deployed in space, I can do things like, send out ships to the place that I'm looking, or I guess you could go light a fire, something along those lines to actually simulate that or elicit an activity. But where the satellites are in space and all of those, the configurations there, they're much harder to completely control. And so your design strategy has to change. In a digital or software in the loop environment, you have freedom to really explore the space. Whereas in deployment into space, you're going to be confirming things that you've learned before and checking for departures from expected activities. So we think that's an important part of this test and evaluation framework to consider. Next, we have to think about, well, what's the flow for actually designing tests? And so I'll put this up and then kind of walk you through it on the tables in the next 3 charts. So there's, of course, the phase that we're in. So do we only have algorithms right now, or do we have a full-up system? Those are going to drive, what are we interested in studying in the test? And that hierarchy of tests reflects back to where we were on the previous chart. So we could have, a full-up system deployed in space, and we want to update a machine learning algorithm embedded in that system. That might be at a very, we might start in our digital simulation or our software in the loop, incorporate it there, and then proceed up that hierarchy. Or if we're only playing with algorithms and trying to decide whether a certain computer vision algorithm is the best one for doing tests at sea versus in looking for forest fires, we might want to do all of that solely in a digital or software in the loop level of the hierarchy. So then from there, once we kind of know what we're working with in terms of the system that we want to test and what capabilities we have in terms of the hierarchy, we need to understand what the goal of the test is, and then competing with that is any requirements for test plan efficiency, resource limitations, or risks that are associated with that test plan efficiency. When we have all of that, we can move on to test methods, and I'll show you some examples, and then from there, the test plan. So,
Dr. Freeman, yes. Can I interrupt? I'm sorry to interrupt you. Yeah. There's a message on the bottom of your presentation. You need to hide. It's saying that you're sharing your screen. Hide that.
Oh, I don't. Hide. There we go. Is that better?
Hold on. That's much better. Thank you.
Okay, thanks. Sorry about that.
I'm sorry.
All right. So to move through this, say if we know that we are in the very early phases of our process where we're looking at just an AI algorithm itself. So we're focused on that unit testing of the AI algorithm. We know, though, the mission that it's going to be tasked to accomplish. So it's a computer vision algorithm, and we're going to ask it to look for anomalous traffic and shipping behavior that might be indicative of trafficking events. We know where we might be looking from, across the Atlantic. And so what environmental factors that will drive, what that means for the orbits that we need to be in, all of those things. And so we have both kind of what the algorithm is supposed to do and the knowledge of the environment. So the hierarchy of tests is really going to focus on the kind of simulated inputs in that digital space, because that's all we have. We just have the algorithm. Excuse me. And so thinking about kind of the two competing domains of test plan efficiency versus the goal of the test, we could say the goal of the test is to assess the AI reliability, robustness and performance and biases, coming back to the concept of cognitive biases, that we want to understand what the bias is in our algorithm. And so to get to test plan efficiency, we'll be looking at black box testing of simulated inputs and focusing on bug checking. So that's going to drive us towards the actual test method. And here what we proposed was CIT is combinatorial interaction testing, which is a technique used in software testing to find bugs and kind of cover the space as efficiently as possible. And so in this example, we said, let's do some of the combinatorial interaction testing on all of the environmental conditions we can think of in structure. And then from there, we'll use optimal learning to ensure that we've got the input space coverage and that we minimize unknown performance areas. So that's the process that we would go through to define this first phase of testing. Second, in the next phase, we might think about, okay, well, now we're going to integrate that computer vision algorithm onto a satellite that's going to be charged in connection with other satellites looking at accomplishing this mission. So here we're focused on systems integration testing. So everything that we thought of before is important. And additionally, so in terms of the algorithm's goals and its performance, but additionally, we have to consider the integration testing aspects of the electronic hardware and any of the mechanical systems. So now to really be able to do that integration testing piece, our hierarchy of tests is driving us towards more hardware in the loop, where we're actually looking at the sensors, actuators, control software, in addition to that algorithm. So not only do I have my computer vision algorithm, but can I go get the inputs from my sensors? Can I move the satellite into position to get to those things? And we might be doing that in a hardware in the loop, or even deploy one algorithm upload into space and see if we can do those things. So now when we think about the trade-off between the goal of the test and test plan efficiency needs, we're more interested in assessing the system performance, reliability, cybersecurity, all of those things while the system is deployed in space. And we're going to focus on, because we've already really fleshed out what the algorithm is doing, we're going to focus on covering the interactions between the systems and its deployment onto the algorithm and its deployment onto the actual systems to identify any faults or performance drop-offs. And so here we might use something more like classical design of experiments, using known software integration areas as the environmental factors as the things that we vary in our test design. And we can take this up to the next level. Say we take the whole constellation as is and replace it with a new smart cognitive constellation. But we're going to have humans integrated on the loop looking at that. And now kind of we take this whole process up one more level where we're really focused on the operation and the ability to accomplish the mission with this new human agent team. And so everything that we considered before still is a factor to consider in terms of our field of study, but we also need to think about the psychology, the human-computer interaction, the artificial intelligent agent teaming constructs. And so, of course, now our hierarchy of tests is really everything on our use case. It's satellites, it's the ground station, it's the operators taking information from it, and the environmental conditions. And here we might look at design of experiments with human factors as the kind of pieces that we're varying to make sure that we understand performance and the ability to accomplish this mission. And so what I hope I illustrated there is kind of a process at a very high level, like I haven't put the test designs out there or anything like that, but also kind of with the goals of the test changing, how performance measures and the factors that we consider in these tests changing as well. And so with that, I want to transition into more of a deep dive on what performance measures we need to facilitate test planning on this regard. So going back to our system of cognitive agents that we're thinking about, I'm going to drill down into the specific agent, the flight controllers that we're looking at that are saying, here, satellite number one, you need to make sure that you're looking at the forests at this time, and satellite number two, you go there. And so the flight controller is really the agent that we're looking at to say, you're the one in charge of accomplishing this mission, but there's lots of other agents that we kind of fleshed out as we went through this. So maybe within each flight controller, they have a mission manager. That mission manager might be in charge of turning on and off the sensors, the actuators, making sure they're in position and that the sensors turn on at the right time. A processing agent might be taking all the information that they've collected and feeding that back in to the flight controller to say, yes, we got the information that we needed, or no, we didn't. You need to replan and go get more information. all of these satellites might be supported by a recovery agent. So if a satellite goes down, a recovery agent might come and do troubleshooting and try and fix it. And then there's kind of the larger orchestration at the high level, like how do we orchestrate all these satellites to be in the right place at the right time? And that might be our movement agent. And so there's lots of different agent types in this system of cognitive agents to consider. But we know the mission that we're interested in, which is look for fires in the southwest or northwestern United States during the summer. And so from that overall mission, we can decompose the system level tasks for each of our agents into different bins here. So for the flight controller, you can see generate an observation plan, so figure out who needs to be when and where. Create the schedule for all the spacecraft, send the data to the appropriate agents and stations, develop the data and commands that should be received and unpacked. And then the movement agent might be saying, okay, make sure the spacecraft is in position at the next observation location. The mission manager is saying, make sure you get the desired data. And the processing agent is saying, yep, we saw a fire and we know what to do next, or we don't. And then finally, we already talked about the recovering agent. So the point is that we can decompose this larger mission that these systems need to do into these subsystem level tasks. And now that we have the tasks, which in the overall mission, we can start to think about what performance measures are going to be meaningful. So at the highest level, even if you know nothing about the system that you have, but you know what you want it to do, that's kind of the mission, that task level that I just described. You can come up with things that will measure how well that you've done that. Now, if you don't do it well, or if performance drops off, how do you know what caused that performance degradation? To get to that, you're going to have to drill down into the next layer of what's going on. So what are the functional architecture of your team? So we might have the agents and a team of agents, and then below that, there's each individual agent and the cognitive functions or the AI algorithms that we've embedded in them. And then at the lowest level, there's the physical implementation. So one of the things we thought a lot about is how low do you go in your performance measures, and how low can you go if this is, a US government agency that is maybe buying some of this from a contractor, and they haven't bought into all the IP, right? So they might not know exactly what the physical implementation looks like. And so our approach was to define performance measures in kind of all of these levels. And then here what I'm illustrating is at the team level, we might know exactly how they're structured, right? So we might have this whole information of what the teams are, who they are, what their specific tasks are. And so at the team level, it would be white box. But at the agent level, we might not know the specific implementations of the machine learning algorithms, so we might not know how they're fully implemented. And so that agent level could be black box, or we could be black box kind of in terms of within each agent, what are the actual components within the agents or the physical implementations of those. And so the onion model is how we went about thinking about performance measure definition. And we said, okay, well, we know, as long as we know what we want the system to do, we can always do the mission level. And then let's decompose as low as we can so that we can kind of troubleshoot in our performance measures. So we took a block diagram approach, saying if we know the task or the mission that the system has been given, we can break that into several subtasks with specific goals. And those goals are the desired discrete end state. So we can measure against those goals. The objectives are the criterion on how well that goal was achieved. And then any constraints that we might have were considered. And so we can, from the subtask, we can decompose down into the action space. And we know that those subtasks might be solved by different methods. And if we know the method in particular, we can say, collect data on that method. But if we don't, we can be collecting data at the action space. And from those, we said, we want to collect data to understand what happened, but also we want to collect data for the performance measures. And so we decided that performance measures in these systems were going to be the things that really achieved the goals of those subtasks across the action space. whereas any other data collected might be meaningful, but it really is only useful for kind of causal analysis when things go wrong. So that's just kind of a high level of our process, as well as the jargon that we use to really tell ourselves what was a performance measure versus what was just extra data collected, and really focusing on performance measures being those key variables that will tell us how successful we were. So this chart summarizes the performance measures that we developed for this use case using kind of our onion model. Here we assumed that the specific implementation was going to be black box, but that we knew everything else because we kind of designed, I mentioned earlier, we had someone who was really focused on satellite orchestration and the different types of satellites. So she helped us really flesh out all of these agents, what they would do, how we would actually execute this. And then we had people on the machine learning side that said, okay, well, if you were trying to achieve this, I would probably use a rule-based approach. Or if you were trying to achieve this, I would use a computer vision algorithm. And these are popular ones. And that helped us figure out what the right types of performance measures were at everything from the mission all the way down to the individual agent level. And so you can see here under our onion model, you can see that the topmost layer of what we would review in terms of performance measures. And so, of course, there's always kind of the mission success piece here. We're looking at detecting fires. And so we define that mission success as the percent capture over actual. There's canopy, you can say, okay, I want you to be looking at this area of the canopy. So that's our canopy coverage completeness. And then when fires actually exist, we want high classification accuracy. So what was the precision? What was the recall in fire detection? Now, a satellite isn't just going to sit over that one area. They have to pass to the next satellite. So that pass piece is a point of interest in the mission. So that's our probability of tipping success. Did I successfully pass, and was the information, and the next satellite was able to pick it back up? A track completeness. So did we at any time lose situational awareness of where that fire was, what area it was covering? And then, of course, at the highest level of the system, we need it to be available. So all the sensors need to be working when we tell them to turn on and collect data. So system level availability, as well as all the components of the system. And then if we were to lose the system for any reason, a system recovery timeliness. We thought were all kind of critical things for that mission level. Now, when we decompose down into the team level agents, you can see here, some of them we have NAs. The mission manager, the way we designed the system was fully embedded in the flight controller agent. So it's not really a team. Anything that the flight controller was doing was teaming with the mission manager. So we captured those performance measures over there. And then each of the agents themselves. So let's take that mission manager to go into a little bit more detail. There, so the flight controller would say, we're going to go to this area, and I need you to collect this much information. The mission manager would then turn and say, yep, I can do that. They'd assess their power supplies and say, yep, I can turn on the sensor for that long. And so then, so the duty cycle of the sensors, the error and any predicted versus actual power draw, and any errors in the observed area versus the desired observed area would be reflected on the mission manager agent. And so that's kind of how we would have the detailed information that if say we didn't meet the percent capture rate that we were hoping for at the mission level, we could drill down to the mission manager agent and say, well, what happened? Oh, well, they thought they were going to have more power than they actually did. And therefore we lost the last 20 seconds of capture opportunity. Those are the types of things we want to be able to say by having this multi-onion layered kind of performance measure capability. Right. So I'm going to wrap up with kind of what we have done this year, and then how we think we should be moving forward in this types of work. So in the first year of this research with our collaborators at Purdue, we developed this overarching framework for thinking about test and evaluation of these complex intelligent agents deployed in space. We developed some specific case studies with The performance measures I've shown you here are really just a small subset of a much larger set of performance measures. And so we've developed case studies on how we would go about extracting those based on this mission system architecture down to the agent configuration. And we also initiated research. There's a lot of research out there in kind of human agent teaming. And so thinking about how that would be adopted into this world of intelligent agents is another area that we focus this year. So all of this, one of the things that I think the team was really struck with as we were going through this process is that this is really hard to do in the abstract. You really need a system to do this. So the things moving forward that we're recommending is that we needed a comprehensive test and evaluation program in thinking about this stuff. And I think you're starting to see that. One of the documents that came out over the summer from the IC community that I think that was very interesting was their IC, or the IC's artificial intelligence ethics statements. And in there, they actually specifically call out the need for a test and evaluation program and what it should do. And so this is kind of our team's reflection on that test and evaluation program, what it should do. But basically, this is, in my mind, the government's way of assuring that they have the information that they need to make decisions. And so a test and evaluation program at its roots is really just a process for collecting data to support decision making. So we need the ability to define these performance measures and figure out what data we need. Also, the framework gets at what's a sufficient data collection to meet the goals of that test. And then starting at the very beginning of system design and development, a test and evaluation program should be informing decision making from how the system is structured, what is the best algorithm to plug in, how do we design for robustness, all those kinds of things can be informed by data collection and test and evaluation. And then as our system matures, the test and evaluation program should provide an understanding of performance growth or degradation. As we move into operationalizing or deploying the system, we need to be able to characterize performance as a function of these different environments. So as we transition from looking at ships at sea to fires in the United States, how do we change in our performance? What do we do to keep performance high? And then at the highest level, the ability to make predictions about future events and tasks and quantify risks in any of those decisions is a really important capability, because that will tell us that's going to give you the confidence to start to actually adopt and deploy AI algorithms into these complex systems. So we expect that given a lot of what's in the strategic visions for the DoD, the IC community, that and the government as a whole, that there's going to be a high priority getting capabilities like this into space and into complex systems in the very near future. And so because of that, we think test and evaluation is this fundamental capability that will inform that decision-making process. But as I was highlighting before, our struggle here is without the actual system, how you develop these methods and processes is a little bit kind of hand-wavy, and we make up our own systems and think about that. And so I think future work needs to move in really 3 strategic areas. So first of all, you just got to go out there and do it. And so we need to think about how we implement and integrate with this performance measure work and the test and evaluation framework work with actual programs doing these things. And so we're working on that piece. Even if they're not, the full up constellation of satellites, just that first deployment of an algorithm, let's think about how to move through that. Also, I think we identified that there's room for expansion and refinement of performance measures for these agent teams, especially when thinking about cognitive agents in the teams, and reflecting on the more specific cognitive architecture. So that's that inner circle of the onion. And then finally, we need to progress in kind of the design, test, evaluate, design cycle for these cognitive agents or agents, including machine learning algorithms. How do we do the trade studies that allow us to play with the engineering configuration and the algorithm that we choose to kind of choose robust solutions? And then finally, as part of that closing of the loop, the ability to kind of predict to the future and then confirm that you got there is the online test and evaluation capability that is needed. So with that, I will stop and leave time for any questions.
Great. Thank you, Dr. Freeman. That's a great talk. So we have a question on how do you integrate the AI algorithm updating or learning in contrast to traditional verification where the results are very repeatable?
Yeah, that's a great question. And that to me gets to the ability to predict the future and then verify, because that machine learning algorithms, that to me they're software plus variability. So we know how to deal with variability, though, right? We've been testing humans, and humans are highly variable creatures. I don't do the same thing on a day-to-day basis. I swear I gave a practice talk of this talk last week, and it's totally different this week. I don't really know what happened. But anyway, we know how to deal with variability. We have design structures set up for that. And so that's, I think, an area where we have to test sufficiently so that we can characterize that uncertainty. And there I look to a lot of what the quality control group or industry has done and design for quality. If you test enough so that you can say, here's, on average, and here's, the variability that I expect in that, then your verification process becomes, can I predict a future value? And if I can, that means that I understand that algorithm well enough that I feel confident, using it. And so it's moving towards more statistical based frameworks for software verification is, in my mind, one of the ways that we think about that.
We also have another question in a similar line about how can uncertainty be included in metrics for the AI's outputs?
That's a great question. And I've been contemplating, so testing, before ending up at Virginia Tech, I was working on testing military systems that are operated by human operators. And we will often have requirements that were, do this 80% of the time. And it was like, well, what if it was, 79%? Was that good enough? Or how do I know that 1% difference wasn't due to uncertainty and just the amount of information that I had? And so one of the solutions that was thrown out there that I don't think works is, well, let's just, assign a confidence value to that. Well, I want 80% confidence that it does this 80% of the time. That just results in people backtracking requirements and coming up with a new requirement that puts a lower confidence bound there. And so you've essentially just raised the effective requirement. I think some of it is just being okay with uncertainty and maybe having requirements that are, I don't know. I actually think it's kind of an impossible question, and maybe the better solution is to not think about requirements as hard and fast. I like to say that, test and evaluation has to change from a summative evaluation to an informative, right? It should always be about supporting decision-making and not hard and fast rules that are pass-fail. And so having people that understand uncertainty, a workforce that is empowered, that's one of the big challenges, that we're often not empowered to make decisions in the context of uncertainty. And those to me seem to be better solutions than trying to add some kind of uncertainty requirement in addition to the requirements that we already have.
Well, that is the extent of our questions. So we have 1 minute until the broadcast ends. I really, really appreciate your talk today. I'm sure the others do as well.
Perfect. Thanks everyone for attending. And thank you, Tyler, for chairing and bouncing from room to room today.
I'm happy to.